Hello, everyone, and thanks a lot for the invitation and for organizing this nice series of seminars. So indeed, today I would like to talk about a connection between the vacuum S matrix and how to use the S matrix to extract thermal observables. All right. So this is a working collaboration together with Pietro Baratella and Emanuele Gengi, and we put out two papers in the last couple of years. And in parallel, when we put out the first one, it also came out this one by Daniel Schubring, which is also, I think it's an interesting paper, so you may have a look at that one as well. All right, so what's the deal? Okay, normally we may look at some action formulation of our theories, out of which some observables follow, like the S matrix or the finite volume spectrum. And a natural question is whether there's a simple way to bypass the action and connect or find relations directly between different physical observables. And well, for instance, if we look at the finite volume spectrum, there's a very definite answer to this question, at least in the elastic regime, that connects the S matrix with the spectrum at finite volume. And this goes under the name of asymptotic Bethe Ansatz or Luce's formula that perhaps or probably many of you have seen. And an heuristic way of thinking about it is that you consider the wave function in a large but finite circle. And so you consider, for instance, two particles. The two particles can occupy two positions that are well separated, but when the particles cross each other, they can get you need to take into account some phase shift because of the crossing. But then we should remember to put some boundary conditions, some periodic boundary conditions, and this leads to this nice relation, which goes under the name of asymptotic Bethe Ansatz, that quantizes the spectrum of the third finite volume in terms of the phase shifts, right? So, however, more generally, well, needless to say, well, we can take the log of this, and the general form that this equation is normally represented looks like so, all right? But more generally, we can think that when we are looking at the S matrix, if you look to the left, we are looking at diagrams that look like so, like when it is a 2-2-2 scattering. While if we look, for instance, the simplest one of the simplest thermodynamic observables, like the free energy or the vacuum energy at finite volume, at least in perturbation theory, it typically looks like so, where we are computing a bunch of vacuum loops. So it doesn't take out of imagination to imagine that to go from one to the other, we are sort of tracing over the diagram. Okay. This may sound naive, but this intuition is indeed realized, and it goes under the name of Dashen Bernstein equation. That what it achieves is that, if you wish, it encodes. It shows that of course, the fact that the thermal observables like the thermal partition function can be excited from the S matrix should not be too surprising, because at the end the full S matrix contains all the microphysics. But perhaps what is somewhat beautiful, I believe, is that this encoding, the fact that we can encode the thermal observables in the S matrix, takes this very particular and simple form. Okay, that's quite nice. But we'll see along the talk that this equation, however, even though it looks very simple, there are a bunch of subtleties with it. Okay. one of the main subtleties is that because of this trace, because we are tracing, we are basically taking the forward limit of the full S matrix. And this can lead to a bunch of IR divergences. Okay. And this is what precluded progress with this equation. So for many years, this equation was only used at a leading order in perturbation theory, because as you go beyond, even in theories that are infrared finite, this formula appears to have IR divergences that are supposed to cancel. So we'll see that in theories that there are no IR divergences. This energy dependence of the equation is key to resolve the IR divergences. While in theories like QCD that do have IR divergences, we'll see how to treat them using this equation. Okay? We'll see that there are a bunch of resummations that one can do that solve those IR divergences. So if you wish, this will be the main message that I will try to convey in this talk. Okay. So before we go into details, let me make some simple comments of this equation, and then we'll go through examples and derivations. Well, needless to say, because of unitarity of the S matrix and this basic identity, the integral in the equation is purely imaginary. It's a purely imaginary function. Okay. And because of this I complex I, it's an explicitly real equation. Now, this operator here, this S operator, is the full disconnected S matrix. So it contains disconnected elements, not necessarily connected. Well, this equation also gives us a representation for the density of states based from the S matrix. Then what we'll see later on, but here we can see it pictorially, is that the trace is what is generating the well-known thermal circle. So you can imagine that particles travels around the cylinder, and they interact a number of times. And so the trace plus the Boltzmann weight, we'll see that generates the particle number densities that we should expect to appear in terms of freestyle. Well, we'll see that now I will derive very quickly this equation, and we'll see that formally it's valid on any space-time that can be factorized like this. So we'll have a thermal circle plus some space where we can define our Hamiltonian. And maybe I should say that one of the applications so this equation was highly cited in a context of the so-called hadron gas physics, and the people were citing this equation because it addresses a simple physical question, which is the following: imagine that you have a very long-lived particle, okay, but it's not asymptotic. It's not an asymptotic state, okay. So should you add it when you count the entropy or when you count your partition function? So the intuition is that if it's very long-lived, yeah, you should count it. But if you wish, this equation gives you a precise argument for it, which is that if your asymptotic particle, if your unstable particle is this particle being exchanged, what you obviously see is that when you take the trace of this matrix element and then you take the narrow width approximation, this is going to become a delta function that clicks on the particle density distribution. And well, before this works I'm presenting today, I think it was mostly used in non-relativistic context and at tree level and for two particle states, namely at leading quarter. But as we will see now, it actually makes sense also in the relativistic system and for many particle states, which will be the main derivations. Okay. Now, as we saw, this equation was first written in the 69. So we may ask, why do I want to look at it right now? So there are a number of reasons. The first reason, and was the original motivation I had, even though then I found other interesting applications. The first motivation is that in the last years, we have developed lots of bounds on the space of effective field theories by bounding Wilson coefficients. And these bounds are typically found by analyzing axiomatic properties, if you wish, of the S matrix. So analyticity, unitarity, and crossing. So one natural question is, how can we map these bounds on in the space of Wilson coefficients into bounds into the space of thermodynamic observables? So it could be like some derivative, the derivative thermodynamic quantity like heat capacity or speed of sound. We would like to see some back and forth talk about among these two types of words. This is not wishful thinking, and we have concrete examples already of these two arrows. Okay, so one is very well known from a few decades ago, where in the context of cosmology, people was considering the so-called P of X theory. So these are theories defined by a Lagrangian density, which is a general function P of X, where X is the kinetic term. All right, and people would just write some graph for P and use those theories to do the so-called Gauss condensation, where this X will take expectation values and not trivial values of this P function. But then people soon after realized that that there were bounds that you could derive by asking that in some general background of X, the speed of sound is smaller than the speed of light. Okay, and this constraint on the speed of sound implies that the functions that you can consider P of X must be convex. So this is a bound that is not about that it's a general property of P of X, not a bound on a single Wilson coefficient, but it's a more inclusive bound, if you wish. Now, on the other direction, this perhaps was the original motivation for me to look at the DMB equation. A few years ago, together with these collaborators, what we did is the following. We analyzed a system in 2 dimensions that describes the scattering of gallstones in a long flux tube. Okay? And for reasons I will not derive today in detail, this is interesting so this describes string-like excitations and is interesting in the context of the problem of confining. All right? But here, the only thing that we need to, for the purposes of this talk, the only thing that matters is that we are scattering gallstones in a line. Okay? And when you scatter gallstones in a line, for this system, at leading order, the scattering matrix looks like this. Okay? And using the properties of analyticity and crossing, we could derive a bound on this coefficient. Okay? And the bound on this coefficient can be translated into a bound on the vacuum energy of the system. Okay? But in this context, because we are still in the elastic regime, we could do it using the asymptotic Bethe ansatz that I briefly mentioned at the beginning. Okay? But you could ask more generally how you would do it when you look at subleading orders. So you look at higher orders in this expansion, then you access an elastic regime, and you can no longer simply use asymptotic Bethe ansatz, but you need a formula that will incorporate particle production. Okay? So the formula I'm reviewing today would be a way to extend these results by including particle production. Now, another interesting motivation for what I'm saying is that in the last decade or so, there were lots of progress in understanding the QCDS matrix. Okay, so in principle, this progress could be recycled and now extract thermal properties of QCD. I will review later today what are some of the open problems with thermal QCD. And then, well, obviously, of course, if we don't have the action, the method shines because we can go back and forth between the options, right? Now, so this concludes introduction. Any question here? Or the motivation, if you wish. All right, so let me briefly go through the formal derivation of VMB, right? So the formal derivation is very elementary. So we start with the definition of the thermal partition function, okay? For what I'm going to do next, we can turn to zero the chemical potential. It's not an essential matter. We can turn it on and off, and it's not going to modify in any essential way the rest of the talk, okay? But for simplicity, I'm going to put it to zero, just to avoid too much clutter in the equations, okay? So the very basic step is that we simply introduce a resolvent, all right, here, of the delta function. And then this becomes an identity, okay? A simple identity. Now, let me introduce a bit of notation, which is these resolvents, the G of E and G of G naught, okay? In terms of the full Hamiltonian or the free Hamiltonian, okay? Now, here I always get a question of what do we mean by the free Hamiltonian and so on. So here we are imagining that we can partition the Hamiltonian into a solvable part, which it may well be the Hamiltonian that acts on the asymptotic particles, the focus space of the asymptotic particles, and an interacting Hamiltonian, very much so as in the Liebman-Schwinger derivation, okay? Now it's a matter of algebra to show that under the trace, these two resolvents, okay, can be related to the S matrix. Okay? And the idea is the following. First, we need to, so this basic, if you wish, non-relativistic scattering theory, that you can write the S matrix as the product of these two Meller operators, which these Meller operators do half of time evolution, and the other one does the other half of the time evolution. Okay. And now, given this definition of the S matrix in terms of the Meller operators, we just plug it here. So we differentiate with respect to the energy, and we take the S inverse, and there under the trace, now it's really simple algebra, you will see that it gives us this linear combination of resolvents. Okay, and this linear combination of resolvents is nothing but we had in the previous slide. Okay, so this is roughly the derivation, and then finally, assuming some nice convergence at infinity, we can replace this differential by some logarithm of the S matrix. Okay, so this is the gist of the derivation. Okay. Now, it's elementary, but we'll see later that there's a small subtlety, and this will come later on when I present examples, between taking the trace or taking the epsilon to zero. Turns out that these two operations do not commute. And if we look in detail in the derivation, what we're instructed to do is to first do the trace and then the epsilon to zero. Okay, we'll see. We'll see it later today. We'll see a paradox if we don't do these limits in the correct way. Okay. Now this is the partition function, but often we are interested in the free energy density. So how do we get it? We take the log. Okay. And when we take the log, basically we get the same equation, except that we need to take the connected part, or you will the extensive piece. Okay, we need a single power of B. Okay, and here there is another small, if you wish, subtlety or something that is not very commonly seen in particle physics, at least, which is that here the connectedness is on the trace. Okay, not on the S matrix. So, and this I will show it in the next few slides. Namely, we should take the trace of the full S matrix, which may contain connected and disconnected matrix elements, but do it in such a way that we only take those elements that get connected after the trace. This may sound complicated, but it's very simple. I will show you in a very elementary example next. Okay. So this will be the main object for analysis in the next slide. Okay. So let me go now through applications of this equation and the recent developments that we have done. Okay. So let's start with the simplest thing, which is the free theory, and this will show us what do we mean by connectedness in the trace. Okay. And doing this in detail is useful because when we go to interacting theories, these rules that we learn for the free theory in terms of the connectivity stay the same. Okay. So because it's a free theory, here we put the free Hamiltonian, okay, and we are just taking the trace. Okay. So the picture is the following. So we have 1 over n factorial from the exponential, and it's useful to draw some pictures. So we have these 1, 2, 3, 4 particles that are traveling along the cylinder, and the trace instructs us to identify them with the 1, 2, 3, 4 particles, right? And this we can do it in a number of ways. So one way is to connect it. So namely, we identify this line with this line, this line with this line, this one with this line, and finally this one with this one. And these are connected, right? So this one will generate a single delta power, okay, which will be interpreted as a one volume factor. Instead, disconnected traces are things like so, okay? So we connect these two pieces like this and these two pieces like this, okay? So very simple. And now we can just do the calculation for the free theory. It's a basic, it's a basic result of thermal free theory, but done in a slightly different way. And you see, there are n-1 equivalent ways to connect something, because let's say you connect one with some guy, then the next guy, let's say the one that you connected, you only have n-2 left, because you cannot connect it with this one. So you cannot connect it with himself, which is occupied, but not with neither with the previous one, because otherwise it generates a disconnected piece, right? So clearly, this generates n-1 equivalent ways, which cancels the n-1 factorial, and this gives us the log, which is the very famous way of the very famous leading approximation to thermal free theory, right? Which is simply a vacuum loop, very simple. Okay, this is very, very simple, but we see a small element of simplification with respect to the usual way of doing the calculation, which is that because of the way we are doing the calculation, we should only be counting physical particles. So if we were doing this for QCD, we only need to multiply the result that we get by 2 times the number of polarizations times the number of degrees of freedom. The standard textbook calculation instead will instruct you to compute these 2 loops, and you will get the one from gluons minus the one with ghosts. Okay, so it's slightly less, it's slightly more off-shell and slightly more physical. This is a tiny simplification, but now we'll see that in higher orders it's simplified way more. Okay, now we know what does it mean to be connected. So now let's add interactions. Are we all on board? Yes? Okay. So it's basically the same idea. So now we expand the logarithm and let's work at leading order in T. Okay, one insertion of I'm doing the usual stuff where we divide 1 plus I some delta function T. Okay? And now we expand the log, leading order, we get a power of T and a delta function. Now, I'm not going to prove it today here, but you can find it in the paper. It's just a bit of algebra that if you take the connected pieces, Namely, now we consider diagrams of particles flowing around the cylinder, and we allow them to interact them once. It's not necessarily 2 to 2. This T means one insertion of T. It can also have 3 to 3, but one single T. Okay. Plus spectator particles that fly around. And now you take the connected piece of these whole things, you'll see that what you end up getting are simply the particle number densities. Okay? This is a well-known formula in the literature, but the DMB will instruct us how to go to higher orders. Okay? Now, let's see how this equation works at a leading order. A natural way to apply this equation is in Young-Mills or QCT. And here we will see that it really simplifies with respect to the usual off-shell imaginary time formalism. So we need the forward matrix element because now I want to apply it at leading coordinate alpha S. So we need a single insertion of T, and we need only 2 particles if we want alpha S. Okay. So alpha S is GS squared over 4 pi. And you see, let's look first at gluons. So you see the diagram I'm thinking of is I have 2 gluons, right, that enter, and we need to trace over it. No? And because we need to trace, I look at the general 2 to 2 gluon amplitude, which looks like so, and I take the forward limit. Very simple. So if you take the forward limit, this amplitude reduces to a simple R number, so some real number, which is given by this. G squared times C times C squared minus 1. So then the equation collapses. It's very simple because this becomes a number, okay? And we only need to iterate over the particle densities. And these are a simple analytical calculation. There are no scales, so it's simply going, the only scale is the temperature, and okay, you get this result, which, needless to say, agrees with the actual calculation. I mean, with the standard textbook calculation. The standard textbook calculation instructs you to compute these 3 loops. Okay, when you add these 3 2-loop diagrams, you land on this calculation. Okay, and here it's somewhat simple. Now, of course, we can add matter, and here is an interesting small observation, which is the following. Again, the forward amplitude is a simple real number given by this. So we can plug it in the formula. We only need to do particle densities integrations, and we end up with this simple factor, which of course is with the literature. Now, here there's something interesting, which is that at leading order, say in QED, we have a singularity. There's a forward limit singularity. Okay, but because we have this diagram and the one with the antiparticle, the divergence cancels. Okay. And in QCD, this happens because we have antisymmetric structure constants. Okay. If we were to add a chemical potential where we weigh different charged particles, this cancellation doesn't happen anymore. All right. So this is the calculation up to this order, and next I would like to discuss this order calculation, and this is the state-of-the-art calculation in QCD is up to this order. Okay. All what goes beyond are resummations of this order. Okay. But here, let me review very quickly what is the status and what are the very well-known problems. So when you go to the next order, we'll see that there are IR divergences, and those are physical. Namely, those are due to the screening of the propagating degrees of freedom. Okay. So we'll see that we know that leading order for the propagator, this loop generates the so-called Debye mass, which is in the electric components of, say, the gluon fields. Okay. And this happens at this order already. As we move to higher orders, there are non-perturbative IR divergences, this is so-called Linde problem, and those cannot be cured in perturbation theory. So there are two equivalent ways of seeing the problem. One simple diagrammatic way of seeing it is that if you do some power counting, you can see that these vacuum diagrams, these ladder vacuum diagrams, contribute like this. So effectively, there is an expansion parameter, epsilon, which is g squared t over pi times some mass scale. Okay. Now, the by mass, which screens the electric components, goes like g times t. Okay. So if you plug it into this effective expansion parameter, it gives you a factor of g over pi. So if g is small, you can still reinstate perturbation theory. Okay? But it's easy to see that up to this order, okay, there is no contribution that would screen the magnetic components of the gluon fields. So therefore, the scale that gaps the magnetic components is smaller than this factor. So if we put this factor on the effective expansion, we'll get an order one number, and therefore there is no way to reinstate perturbation theory. Okay. Perhaps a more clarifying way of seeing the Debye problem is, of course, with simple effective field theory, where if we do dimensional reduction of the thermal circle all the way to get the magnetic, the magnetostatic components, we'll get this magnetostatic times 1 over t. This 1 over t is simply from iterating out the circle. But now you canonically normalize the fields, okay, by sending A to, the gluon field to the gluon field times square root of t to cancel this. And you get the effective magnetic coupling. And therefore, by dimensionalize, the free energy goes like this power, okay, which is the same as the one that we see for this diagram, okay? So these are the diagrams that led to these non-perturbative effects and appear first at for loops, okay? And they are, of course, resolved by the fact that the three-dimensional theory is gapped, but it's non-perturbatively gapped. So it's not calculable in perturbation theory. A speculation that I will say at the very end of the talk is that perhaps using this equation, we can devise like inclusive observables from the S matrix that can sort of make this problem milder. Okay. Now, last year there were these nice calculations where from Lattice Monte Carlo, where they pushed the free energy calculation, the equation of the state of QCD, to relatively large energies. And I'm highlighting this slide because these so numerical calculations are getting to high energies, but at these scales where alpha QCD is roughly 0.1, still perturbation theory from thermal QCD converges very, very badly, because here we can see the various orders of the calculation. So far, I showed you this very quickly, okay? This one I'm going to show you later today, how is it done, okay? And this is the state of the art at fixed order, okay? Namely, the HT-NNLO is basically incorporating effective field theory resummations, okay? And then at order G squared, as I just reviewed, is not calculable completely. Only a few diagrams can be computed. Those that don't have this non-perturbative phenomena side. All right. So, but before making these comments, I want to make out QCD because that's much harder, and in the sense that it's full of indices and much more cluttered equations. I would like to first push DMB to large orders in a much simpler model. Okay, and this part of the message today is so I think something that we didn't have in the past is a simple model where we would test DMB. Okay, And by a simple model, I mean a model for which we know the S matrix, we know the partition function, so we know both sides of the DMB equation. Also, there are no physical IR divergences, so in that way, we are sure that whenever we hit an IR divergence, it has to cancel. Okay, so we should be careful. We should work hard to be sure it cancels. And then, okay, even better, we'll see that we know of a model where the S matrix and the partition function are simple, and it happens to be an interesting model. Okay, so it passes all the checks, and this model I already alluded to, which is the model of fluxes. Okay, so I already mentioned it before, but the mental picture is to think about Goldstone scattering in a line. Okay, I want to relate these two observables, finite volume spectrum and a vacuum S matrix observables. Okay. So what are the both sides of the equations? The S matrix is very simple. It's simply this object here. Okay. So because these are massless particles, we can draw these simple space-time diagrams where we can prepare some particles that move to the left and some particles move to the right. And a key thing of this model is that it can be organized such that all the scatterings happens in a 2-to-2 manner, and each time that the particles cross, they pick up this phase shift that is proportional to these Mandelstam variables. Okay, where Sij means here the momentum of one particle plus the momentum of the other particle squared. Okay. I'm using many S's, but this S means it's a big S, the S matrix, and this is a small S for Mandel. And then the free energy, it's the simple square root formula. All right. So in principle, this is a perfect setup where we should be able to get this free energy out of the S matrix. But you see, when you first look at this example, we'll find a paradox right right at the start, okay? Which is that the DMB equation that I presented to you at the beginning of the talk involves the trace of the log of the S matrix, right? But the S matrix here is an exponential. So the paradox is that it seems that the free energy would be proportional to Ls squared. Yet I'm claiming that the free energy is a square root formula that involves all the powers of Ls. All right. So how can this be true? So as most of the paradoxes in quantum field theory, is it resolved by being careful with the I epsilon prescriptions. Okay. And this goes back to what I said at the beginning of the talk, that what is going on here is that the on-shell matrix is derived by considering generic momenta and then going on shell. While this formula that we are reading to, we are sitting exactly on the forward limit and only after going on shell. So these two operations that you would think they should give the same, they do not. Okay, and let me show you why they do not give the same. Okay, so for it, let me consider the 3 to 3. So I'm looking at the 3 to 3 because I want to get a correction that is Ls to the 4. Okay. So I remind you that in each scattering, we get from this picture, we get an exponential here. But if we expand in powers of Ls, a leading order, the 2 to 2 will be S squared. Okay. So if I'm looking at this scattering, I'm automatically at Ls to the 4. Okay. And but okay, from this general equation, you can just expand powers of Ls, and you'll see that this is the exact matrix element. Okay, so it's very simple. It contains these energies of the incoming particles. Okay, and this is supposed to be a 3. Okay, and but now if we resolve this equation in terms of the underlying Feynman diagrams, we're going to look at what is the most singular Feynman diagram, and it's this one. Okay. And the internal propagator, which is the one here, you can decompose it into a contact piece plus forward and backward propagating advanced and retarded propagators. And the point is that on the support of the delta function, namely on the support of the trace, the old-fashioned propagator, the real part of the old-fashioned perturbation theory propagator, it's given by the derivative of the delta. Okay. Now here, to be more precise, perhaps I should add an epsilon for this equation to make sense. Okay. So this is the equation that is used over and over in this theory that allows to recover the correct result. So if we plug this equation on the trace, then we recover the exact LS304, okay, which is in agreement with the square root equation. And okay, in the paper we pushed to much higher order just to convince ourselves that we knew what we were doing, and the agreement is exact, okay, as you would expect, because there are no physical IR divergences in this problem. Okay, we push it to the order which would correspond in thermal perturbation theory to 4 loops. Okay, in view of a QCD, which would like to eventually go to 4 loops, I wanted to understand what was the structure. Okay, how these contact terms organize themselves, and so it works. Now, in the paper we have some speculations, but I would say that this is an open problem. So these are a place where contributions are welcome. We failed to give an all order derivation. Okay, I think that would have been beautiful. We tried for a while. We failed. Maybe we should go back and think about it. For a while, I had the following dream, which is that the square root equation is the generating functional for trees. Okay. So, okay, now I'm going out of the script. This is not on the paper, but because this is a seminar with 2 people, I can give some dreams I had, some informal dreams I had. So the generating functional, the square root, is the square root generating function counting the number of trees. So my hope was that when the dust will settle, there will be a way of interpreting these diagrams, and I would just be counting the number of diagrams, and I will automatically land on this equation. Okay, and then I will have a beautiful interpretation where the square root had to be there because I was just counting these trees. Okay, this was not realized yet. Okay, because turns out that there are diagrams that do not fall in this category of trees. Okay, but perhaps it can be realized. We don't know yet. Now, going back to QCD. So far, in the previous slides, so let's not mix too much. So far, what I told you is that in systems that there are no genuine IR divergences, this equation is fine. It just works. Just be careful with commuting limits, okay? Because you are supposed to first go in the forward limit and then going fully on shell, okay? And then at the beginning, I show you as an introduction how to retrieve the well-known alpha 0 and alpha s calculation of QCD with this on-shell method, okay? Now let's go to the next order, which will be alpha s squared, okay? So this will be 3 loops in the standard counting of shell formalism, okay? And in terms of on-shell S matrix, we need the 1 loop MHB and the 3-level NMHB next to maximal density violation. These are very well known and simple looking up, okay? Now, what does it happen here? What happens here is that, so I recall you that there is these T-channel singularities, and when we fuse two, um, um, two scatterings, okay, we get IR divergences, okay, due to this propagating propagator. Now, the standard way that this is dealt with is to add a thermal mass. Okay, so the diagram is, so this I'm not going to prove today, but details are in the paper. If you take this diagram of QCD or lambda phi 4, so you take this diagram and you add all the windings. So all the windings, I mean all the spectator particles, and you take the trace connected. You land on this equation, which is IR divergent. Okay. Now, the typical way that you would solve this problem is, okay, we know already thermal field theory. There should be some screening mass. There should be some Debye mass, all right? But doing so would look odd in this formalism because we are just tracing over the S matrix. We should not now change and add a Debye mass. So we would like to see how the Debye mass appears without putting it by hand. Okay? And how does it appear? So the way it appears is that, unsurprisingly, perhaps some of you, what you need to do is you need to resum a bunch of diagrams. So we're not going to add the Debye mass on this diagram, but we're just going to keep going and formally deal with all these IR divergent diagrams all together. So for instance, it turns out that if you take what we call these comb diagrams, because they look like a comb, okay? And now you resum over this subclass, they exponentiate, and they modify the dispersion relation precisely in the way that corresponds to the soft Debye mass. All right. So if you know a bit of thermal field theory diagrams, this is somewhat, in retrospect, it's unsurprising because this you could interpret as some Daisy diagram of QCD. Okay. What is somewhat nice again is that if you Daisy diagrams resummation in QCD is somewhat involved because of all the ghosts and gauge fixings, while here all the input are on shell matrix elements. So this simplifies quite a bit the calculation. So it's hard to do lambda phi 4 than QCD. It's equally hard. Okay, that's something nice. So I'm gonna talk. Okay, so this brings me to the summary. So there's a way to summarize both things I said. Okay, so at the beginning I was posing this question: so whether we could retrieve thermal physics from a vacuum S matrix, and perhaps my answer now becomes more clear of what do I mean. So the answer is yes. So apparent singularities are resolved by the energy-dependent DMB operator. So by this, what I mean is that be careful with the action. Okay, so basically there is a non-commuting phenomena, which I mentioned a number of times. And the second comment is that theories that have genuine IR divergences, it turns out that, as expected, the vacuum S matrix diagrams reorganize themselves to generate a Debye mass. And this we can also phrase it in terms of a non-commuting object, which is also very familiar in QFT. And here the scene that we're committing is changing sum versus integral, right? Because we are in the original formula had this sum, but if we want to do perturbation theory, we need to commute and do the integral at some point. And this is how we introduce IR divergences. All right. Now, as an outlook, something I've been wanting to do for a while, and maybe now it's time to do it, is that in principle, we could do very similar derivation to the one I presented at the beginning to look at other thermal observables. So a natural one would be to look at for instance, at the correlation function. At the correlation function for instance, of two conserved currents, like T mu. Okay. Then what we expect to get in the right-hand side of some thermal or some thermal um, or some thermal correlation function is to get convolutions of the S matrix with a form factor. Okay. Now, this equation has not been written down to my knowledge in full detail, so perhaps it would be nice to write it down and perform some checks. Maybe we could also cross-check it against some exactly solvable models. There's been people for a long time have been pushing the generalizations of the Lucier equation to incorporate particle production. This looks like an inverse problem with respect to these equations I'm writing. So maybe they could benefit from these kind of equations. And the last and more speculative comment I want to finish is that there is this linear problem I reviewed. And so, of course, the canonical way to treat it is to just do some numerical calculation with the three-dimensional action, and then do some matching procedure with for the theory. But perhaps one can devise other methods which are more collider inspired. When you look to more like a jet S matrix, which will have already non-perturbative QCD scale incorporated, and this maybe can lead to another approach to compute the thermal free energy. Okay, so that's all. I'll leave it here.